Welcome back, nerds. Sorry about the voice. We're going to continue our 1.2 journey. Unfortunately, not finishing it today, but we got to do what we got to do. There are a lot of properties of graphs of functions that we have to discuss. Today, the first thing we're going to talk about is boundedness. And boundedness is a feature of the range of a graph. If your range has a top it can't go through, meaning it doesn't approach positive infinity, or if your range has a bottom it can't go through, meaning it doesn't approach negative infinity, then we would say that your graph has some kind of boundedness. So if you have a top value that you can't go through, bounded above. If you have a bottom value you can't go below, bounded below. And if the graph happens to have both a top and a bottom, we just say bounded. Cool? All right. In this picture, because my graph goes up forever, it's not bounded above. And because my graph goes down forever, it is not bounded below. We simply say not bounded. Just like that. Easy enough? Okay. Like I said, it's a property of the range. Because this graph points up forever, it is not bounded above. However, there is a value that it will never dip below. Because this is a polynomial function, we would say that that is its absolute minimum on its range. And it would be a closed, not closed dot, a bracket on that range. The point is, it has a lowest number it will never dip below, bounded below. I want to take you back a couple pages real quick just to show you something. A graph like this, you don't need to remember this, but this is an exponential curve. And exponential curves have horizontal asymptotes like this that they approach forever. So even though it would never reach that horizontal asymptote, that is still a y value. It would never dip below. So a graph like this we would also say is bounded below. I just wanted to make sure that you were clear that it didn't have to be a point on the domain. Or excuse me, the range. My apologies. It could have been a value that the range is approaching, even if it never reaches it. Okay. This graph, because it points down forever, is not bounded below, but because it does have maximum y values, we would say that it is bounded above. Again, it does not have to be a polynomial. It could be a graph that's approaching a horizontal asymptote forever, and then you say bounded above still if there was a horizontal asymptote above it. Or you could have something weird like this piece of spaghetti that has a maximum y value and a minimum y value. And because it has both, we would just simply say that it is a bounded function. Does it have to be weird spaghetti like that to be bounded? No. Again, we go back a couple pages. A graph like this is actually considered a bounded function because you don't know this yet, but it is approaching two different horizontal asymptotes. So it has a y value up that it'll never reach and a y value down that it'll never reach, simply bounded. I just wanted you to know that they come in many shapes and sizes. Yes, Nyla? So for horizontal lines, we wouldn't try to classify them as having boundedness or not because they're one-dimensional, or technically one-dimensional, so it's like, how do you, yeah. I thought the same thing earlier when I was flipping back to this page, showing it to the last, because I had this class second period also, and I thought the same thing. Luckily no one asked there, but yeah, for something like this, we just wouldn't talk about boundedness. Alrighty, so for these two down here, it does say to use a graphing calculator, but I'm hoping that for part A, you wouldn't need a graphing calculator to know what that graph at least looks like, because it's an x squared graph with a positive number on the front. Everybody in the room should know what an x squared graph with a positive number on the front looks like. It looks like a smiley face. Like that. So without graphing it, does this graph have any boundedness to it? Yes, it does. What kind? Lots of voices. Go on. Below. Bounded below. All parabolas will have a vertex. So all parabolas are either going to be bounded above or below. This one points up. So it is definitely bounded below. Now for part B, unless you are a power nerd like myself, I don't expect you to know what that graph looks like. So this one we will use graphing technology. That's not this graph. Just reminding you where your shortcuts are. Alpha, y equals, will get you to your stacked fraction. If you don't have a stacked fraction available to you, then you would need to wrap your entire denominator in parentheses. And hit zoom 6 to make sure that you're on a standard graphing window. Quite the interesting graph, huh? I am going to change the window a little bit just to really get a feeling for its properties. My y values, I'm going to change the minimum to -2 and the maximum to +2. Isn't that neat? Okay, ready to sketch it. And I'm going to hyper exaggerate its shape. Something like that. So does this graph have boundedness to it? Yes, it does. Well, so if you had to say bounded above, bounded below, or just bounded, what would you say as a class? Bounded. Absolutely agree. We have a maximum value will never go above. We have a minimum value will never go above. Below. By definition, if it's a minimum, you're above it. So anyway, we have bounded, just above and below. Ta-da! Neat, huh? That's a fun curve. So boundedness should be easy. I am not going to ask you to know the boundedness of a function unless it's an extremely well-known function, or I'll give you a picture, or I'll give you graphing technology privileges. Cool? I don't expect you to pull this rabbit out of your hat. The next concept that we're going to discuss is symmetry. There are two kinds of symmetry that graphs can have, and they're not on this page right here. This page right here are special versions of the two kinds of symmetries. I'm not going to test you on the two kinds of symmetries. I'm going to test you on what's on this page, but I do want to make sure that I teach you everything and give you the good vocabulary. The first kind of symmetry that graphs can have is called line symmetry. And graphs with line symmetry can be folded in half along a vertical axis of symmetry, kind of like how my hands are, that I have to zoom out further, but like that. So any graph that can be folded in half along a vertical line anywhere is that kind of symmetry is called line symmetry. The special version of line symmetry that we really want to know about is when that line that you're symmetric around is the y-axis. So if your graph is symmetric around the y-axis, yeah, it has line symmetry. All quadratics have line symmetry. But if the axis of symmetry is the y-axis, then we say that this is an even function. Algebraically, being an even function means take any x value you wanted, and you could either plug it in as a negative x or a positive x, and it won't matter. You will get the same y value out. See here, I have a negative x and a positive x. They give me the same y value. When we test for even symmetry with a function, we literally replace our x's with negative x's and follow the order of operations. And after all of our x's being turned to negative x's has been simplified, if we get back the original function, then the original function was an even function. The second type of symmetry that we'll discuss is called point symmetry. And graphs that have point symmetry, you could also say they have rotational symmetry. Meaning, if you were to spin them 180 degrees around a specific point, you'd get the exact same graph. The special kind of point symmetry that we talk about is having point symmetry around the origin. So if spinning your graph 180 degrees around the origin gets you the exact same graph, then we say that that was an odd function. Another way of thinking about it, instead of saying rotate, because rotations are a little bit scary in algebra because they produce non-functions, is reflections. If you reflect this graph up-down, it would be the exact same result as if you had reflected it left-right. So since reflecting it up-down looks the same as reflecting left-right, and there's no way to tell which one happened, that's another way of saying then that graph is an odd function. Cool with that idea? Notice, algebraically, if you want to tell if an equation is an odd function, once again, you replace your x's with negative x's. This time, though, the result is, oh, you just multiplied your whole function by -1. And that's literally what that says. So if replacing your hold on, stop. I can do this. If replacing your x's with negative x's gets you the same result as if you had just multiplied the function by -1, you have an odd function on your hands. I do want to point out, though, that both tests start the same. So everywhere you had an x, you will substitute in a negative x. And then you'll see what happens. Substitute negative x for all x places. And that should be reviewed. But it's okay if you don't quite remember. We ready to put these things into practice and see what's up? Look for patterns and put on our thinking caps? Okay. I left a lot of space down here. I'm going to do A here, B here, and then I'll do C down here. Just for space purposes, so I can write large enough. I told you that both tests require you to substitute. Replace your x with something. Please, every time you substitute, please, please, please use parentheses. I'm trying to set you up for success for transformations in section 1.6, because that's a 3-day lesson, transformations, even though you've seen them at least twice, Algebra 1 and Algebra 2. We're still going to spend 3 days, because I find that transformations is one of those things that most students still don't have a firm grasp of, and they are a powerful tool. So when I substitute for my x, when I replace my x, I'll use parentheses, and I'll change colors. Everywhere I had an x, I'm just going to leave an open set of parentheses, and then say whatever happens on the left happens on the right. So if I fill the parentheses on the left with a negative x, I'll fill the parentheses on the right with a negative x. Alrighty. This says take negative x and square it. That means negative x times negative x. When I multiply two negative numbers, what kind of number am I going to get? Positive, yeah. And anything times itself is just squared. And the last time I checked, x squared minus 3, that is f of x. So since plugging in a negative x did absolutely nothing, we would say that function f is an even function. For part B, same trick. We're going to throw in a negative x wherever we had an x. So where I had an x, I open a set of parentheses. And I'll replace my x with negative x on both sides. We just did this. Negative x quantity squared gives me x squared. But this is negative 2 times negative x. And you guys already told me when you multiply two negatives, you get a positive. So this is plus 2x. And the minus 2 is unaffected. This is not my original g of x. So this is not an even function. So I wonder if it's odd. In order for it to be odd, we would need this to be the result of multiplying g of x by negative 1. Please, when you multiply a function by a number, please get in the habit of wrapping the whole side in parentheses. Why? Because I'm preparing you for transformations. That's why. So if we multiply the whole left side by negative 1, we multiply the whole right side by negative 1. You will have to distribute. Which gives me negative x squared plus 2x plus 2. And because g of negative x is not the same as negative g of x, this thing is also not odd. We're not going to say no symmetry. The reason why is because all quadratics have line symmetry. We're simply going to say neither even nor odd. And I just realized that doesn't say neither, that says nether. We'll just scribble that out. There we go. We don't need any sky squids from Minecraft in our mathematics. No nether mobs here. Okay, so neither even nor odd. Anybody want to take a stab at what thing I could have changed about that formula to make it an even function? Anybody want to take a guess? Educated guess? Adi, what could I have done?
You could have made it plus 2, I think.
Which,
2x.
if I had made this plus 2x? If I had made this plus 2x and then replaced this with a negative x, I would have gotten a minus here. But that still would have said plus. So not quite. Anybody else? If I got rid of what? Okay, if I just crossed off negative 2x, sure. That would have made it even because it would have looked like a. What other thing could I have done without getting rid of anything? No thoughts yet? So no thoughts on what feature of the functions is making the negative not make a difference? If I had made that exponent a 4 or a 2 or a 6, see what I'm doing? I'm describing even exponents. Because even exponents make negative numbers turn positive again. All right. So what would an odd function look like? I'm just going to throw an odd function up here. That function is odd. This function is odd because if I replace my x's with negative x's, an odd number of negative signs becomes negative. And then this negative x would have a negative in front of it, making this positive, which would have switched this sign and this sign. This is an odd function. This is no longer an odd function because replacing x with negative x would not affect that. Odd function, neither even nor odd. So if we're talking about polynomials, so we're not discussing part C yet. Do we think we have finally discovered what the trick is for knowing if a polynomial is an even or odd function? Paul? Odd means if you replaced your x's with a negative x, it would have been the same thing as if you had multiplied the equation by -1. Okay, Jack, what do you think?
The odd equation simply have odd exponents.
In order for an equation, a function, to be classified as odd, every x has to have an odd exponent. And one more thing, no constant at the end. Basically, in order for a function to be odd, you need every term to have an x with an odd exponent. And in order for a function, and these things I'm telling you right now are for polynomials, and you don't have to have this memorized. What I would actually hope is that you accidentally memorize them through practice. But in order for a polynomial to be even, to say it's an even function, you just need all of your x's to have even exponents. That's it. Now let's tackle this fraction. If it didn't have a bottom, if it just said x to the third, what would we say this function has? Odd symmetry. If it didn't have a top, if it was just 4 minus x squared, what would we say? Even symmetry. So what we have here is a rational function. That means x is on the top and the bottom, where they both the top and the bottom have symmetry, but the symmetries don't match. Let's see what happens. replacing all my x's with negative x's. An odd number of negatives gives me a negative. And we've already seen what happens when we do negative x squared. So now that we're here, I'd be looking for a room full of voices, and hopefully it shows up on the microphone. And words I'm looking to hear are even, odd, or neither. So one of those three. Class, what kind of symmetry do you think this has? So not everybody spoke. He says nether. Not everybody spoke. Nobody said even. That's because you can see clearly it's not the same function. But I heard a mixed bag of odd and neithers. I'll go ahead and tell you, it's odd. And the people who are thinking neither are like, but wait a minute, I didn't change the sign in front of everything that was there. And that is why I was very careful about what I said to Paul when he asked if it's odd, all the signs change. I specifically said, when it's odd, it'll look like you multiplied the function by -1. Because for fractions, the negative sign is either on the top, on the bottom, or on the front. All three of those fractions are the same fraction. But this is the one that shows us very clearly that this is negative h of x. So we have odd symmetry here. So before I bring the video to a close, again, I am not a fan of shortcuts, memorizing a billion math rules. I can't even memorize the 26 names of the students in this room right now, let alone all the math things I've ever learned. So if you're trying to do this based solely on memorization, it's never going to work. There has to be understanding, and there has to be tons of practice. The rules, quote unquote, that I taught you about the polynomials, those are not things I want you to try to memorize. Those are things I want you to accidentally memorize. Because after practicing, after plugging in negative x over and over and over again, the patterns end up sticking. However, I will tell you the pattern that I accidentally learned on how to tell if a rational function is even, odd, or neither. This one was odd. The reason why? Because it had mismatching symmetries. Because one part of it was odd and the other part was even, it guaranteed this function was going to be odd. If the top and the bottom have matching symmetries, you're guaranteed to be even. If either the top or the bottom or both have they're not even, odd, or neither, then the entire thing is neither. So once again, I don't want you to memorize those tricks. I want them to show up in your mind by accident, through practice. Matching symmetries for a fraction, even. Mismatching symmetries for a fraction, odd. Boom, every time. Yes, Adi?
Is that because, like, an odd number divided by an even number is always odd, and then, like, an even number divided?
Yes, that's exactly why. But I don't want to do it with even and odd numbers. Think of it more along the lines of positive and negative. A negative number divided by a negative number is positive. A positive number divided by a positive number is positive. But if one of them is negative, the whole thing is negative. Think of it like that. Thanks, nerds.